Hello everybody, and welcome to Conceptual Astrophysics, a series of videos in which we show how to set up and solve simple problems in astronomy or astrophysics. I'm your host, Dr. Christopher Sorolla, and today we want to decide how to figure out the distance and the absolute magnitude of Barnard star. The Barnard star is the second closest star system to our own, and it consists of one star, a red dwarf. And because it's relatively close, its values for parallax and apparent magnitude are fairly well known. So, for example, the apparent magnitude of Barnard star is a positive 9.511, and it has a parallax of 0.5469759 arcseconds. And again, the reason it's so precise is because Barnard star is, for a star, relatively close to us. So here's the questions then. How far away is it in terms of both parsecs and light years? And what is its absolute magnitude? Now, when doing a series of problems in astronomy or physics, it's often a good idea to set up a table of known and unknown quantities. That is, when you read the problem, what is it that you know or facts that are given to you, and what is it that you don't know or specifically are trying to find out? So we know what the apparent magnitude is, and symbol-wise, that's MV for visual apparent magnitude specifically. We also know the parallax of this, and these double slashes here stand for arcseconds. Also, we know as a conversion that 1 parsec is approximately the same as 3.26 light years. That'll come in handy too. What we're trying to find is the distance and the absolute magnitude. Notice absolute magnitude has a capital M compared to apparent magnitude with the little letter m, like that. All right, so how do we go about doing this? Well, the first question is actually pretty simple. What's the distance in parsecs? So distance is simply 1 divided by p if you're using units of arcseconds for your trig parallax. So it's 1 divided by 0.5469759 arcseconds. Again, this formula is specifically set up to find distance in parsecs. Now I'm going to round off a little bit so that we don't go crazy with these digits. You don't need to have all of them, it turns out, but if we do that, that is our distance in parsecs. That seems decently simple. All right, how about the distance in light years? Well, this is a unit conversion idea. So let me write this. Distance is 1.8282 parsecs. Now, there's a couple of ways to set it up. I like to do it this way. I like to take my unit conversion and write it in a fashion that makes it easy to see what we're doing. So we want to replace light years instead of parsecs, so 3.26 light years, Ly for light years, per parsec, like that. And notice what happens then when I do this. I've set it up so that parsecs divides out parsecs, and unit-wise they cancel, and it leaves me with light years in return. So I did that on purpose. And when I do this, and again I'll round off a little bit, 5.9629 light years. So that's the distance in light years. Okay. In other words, almost 6 light years away, and a little bit less than 2 parsecs away. And that is the distance to Barnard star. Okay. What about the absolute magnitude? Well, so there's a couple of different ways to go about this again, but I'm going to use a formula straight up that we can use. That's absolute magnitude is equal to apparent magnitude minus 5 times the log of the distance plus 5, like that. So I simply put in the log of the distance here. Let me show you how that means. So if in terms of numbers, apparent magnitude of Barnard star is 9.511, 5, and log of 1.8282 parsecs. And again, it is specifically set up to use parsecs as the unit here. Okay, you don't use miles or light years or anything else, specifically parsecs, like that. This log, that's what we call the base 10 logarithm, right? In other words, that's finding powers of 10. You can find powers of 10 for any number, not just, say, 10 or 100. You can do that for anything in between. And that's what we're doing here, of course. So do that, and then add 5 at the end of that So when I do a calculation like this, first I will do the log of this number first. So in your calculator, punch in this number. log specifically is the key in your calculator to use. Get a result, multiply by 5. Then you're going to take that number, make it negative, or you're going to be subtracting it. And then 9.511 plus 5 in this case to come up with total. When I do that, I get a result of a plus 13.21 for my absolute magnitude for Barnard star. By the way, this means that Barnard star is actually a very, very dim star, which, if you remember me saying at the outset of this discussion, Barnard star is a red dwarf, which means it is much smaller across, it is much cooler than the sun, much less massive, and ultimately that means it's a lot dimmer. It's much, much dimmer than the sun. Also, if you want to figure this out, each magnitude, as you recall, is approximately 2.5 times worth in brightness, or exactly 5 magnitudes of difference is equivalent to 100 times in brightness. The sun has an absolute magnitude of about positive 4.85, which means that Barnard star is about 8.5 magnitudes, roughly, dimmer than the sun, which puts it at many, many hundreds of times dimmer than the sun. So it's not surprising that it's actually very dim to look at. One more thing I'll say about this, both of these numbers, the absolute number magnitude and the apparent magnitude, which is right there, mean that you can't see Barnard star with the naked eye, unfortunately. Human vision is such that even under the best seen conditions on planet Earth and with the best possible naked eyesight, you can reach about an apparent magnitude of a positive 6.5, which is to say that Barnard star is about 40 times too dim for you to see with the naked eye. You need a telescope. That's a wild thing to say, by the way, that a star that you can't see with the naked eye is that close. Again, remember, it's the second closest star system to us, and yet you can't see it, at least not without a telescope. Which gives us kind of a hint, by the way, going forward, that it's not the bright stars that are the most popular stars. Those popular stars are actually very dim stars that you need telescopes to determine. Anyway, that is our show for today. So, thank you for your attention. Again, your host, Dr. Christopher Sorolla, and clear skies, everybody.